Hey everyone, Keegan here from Curious Engineering doing a continuation. We're doing part 2 of the Digital Logic Lab 1 series from Altera University Program. Okay, so let's take a look at the lab. Just high level, kind of what this lab is asking for is it's asking for you to start to get comfortable with multiplexers. So if that's kind of a new concept for you, don't worry, I'm going to go over some stuff. If you do know that stuff pretty well, then you might want to fast forward. So we'll spend a little bit of time doing some background knowledge on this. I do have a diagram which might be helpful. Again, so what they're also including is kind of bit width. So bit width is essentially just they want a 4-bit width. So we're gonna look at a number that it consists of 4 binary numbers. So those are going to be modeled by our switches. Let me click on that. Okay. So we have 2 inputs. We have an X input on switch 3 through switch 0. We have a Y input on switch 7 through switch 4. And depending on our select or S input, we'll display the values of the Y or X on these 4 LEDs here. And you can tell, they just also want to make sure that you can tell if the switch input is logic level 1 or logic level 0 by this LED here. Okay. So what is a multiplexer? So a multiplexer, the symbol is presented here. The output of the multiplexer M depends on the switch or the select, the S here. If the select is 0 or logic level 0, then X will be the output of M will be X, whatever X is. If the select is logic level 1, then the multiplexer output is going to be whatever the value of Y is. So if it's 0, 1, it will be reflected there. Same for X. If it's 0, 1, it will be reflected there. So here's the truth table for that. So just really clear, saying if it's the switch is off, then M will output whatever X is. If switch is on, then M will put out whatever the value of Y is. So the multiplexer can be modeled by, at the gate level by this kind of setup here. That's exactly what is happening here. So this is really important. If this doesn't make sense, I'm going to go really quickly over some of these gates. So, and again, if you know this, then fast forward or bear with me here. All right. So, second here. Okay. So there's 3 basic gates which they're using in this laboratory. You're using a NOT gate, an AND gate, and an OR gate. So a NOT gate just inverts whatever is put into it. If it's 0, it outputs a 1. If it's a input is a 1, then the output is a 0. So pretty basic. If you look at the AND gate, the output is only going to be true if both the inputs are logic level 1, or if both the inputs are high, then the only scenario when the AND gate will be high is also or is that scenario. The OR gate, it doesn't depend if one input or the other input is logic level 1 or high. The output will also be high. So it's usually on, and as you can see, the only scenario when it won't be turned on is when both inputs are 0. Okay, so in Verilog, how does this look in Verilog? It's just symbols essentially. So a NOT gate is modeled by a tilde, an AND gate is modeled by an ampersand, and an OR gate is modeled by a vertical bar. Okay, let me double check, make sure we don't have any. Okay, so now that we've done that, we've kind of gone over the symbols in Verilog. The lab actually almost gives you the answer right here. So it's helpful, and at some point I already have the code. It's completed and it can be simulated, synthesized, and uploaded to a board. But I'd recommend you kind of give this an attempt first. As a wise professor of mine always said, the struggle is where you actually learn. So it's very true. So give it a shot, and if you struggle, then maybe reach out for help, and I can provide the code if need be. But again, so this is how you model this almost directly. So if you were to compare these 2 things very closely, you'll see that they are equivalent, and that's what will create your multiplexer. So the difficult part, I guess you would say, is how do you do it for 4 different multiplexers? How do you hook them all up so that they all work at a 4-bit width level. So I don't think I missed anything. So just these are usually the steps where they ask you to do additional things. For example, where was it? I think they wanted to just say like, hey, ground LEDs 8 through 4, but I'm not seeing. Okay, so we've done some background, so let's jump into the actual project. Okay, so let's create our project. So let's open up our Quartus Prime, and we want to create a new project. If you have done this before or you watched the previous video, then by all means go ahead. But if there's anything that I'm doing that doesn't make sense, maybe go back and watch the previous video. I'm going to create a new folder. So let's do that. I'm going to call it Lab 1 Part 1, a new project folder. Oh, no, cancel. I almost made an error. We're doing Part 2. Lab 1 Part 2. Okay. And I'm going to name the project just Lab 1 Part 2. Okay. Empty project again. We're not going to add any files this time. We're going to input our own source files. The device we're going to target, again, make sure you have this number handy. You're going to use it a lot. MA5. And I wasn't entering. Fantastic. Let's see. 6. Okay, that's the device we want to target. We're not going to add any specific tools. Here's a summary, and we're just going to create it. Okay, so we want to create a new source file. We want it to be a Verilog file. And I'm just going to, I already wrote this, so I'm just going to drop it in there. So as again, what you might have been thinking actually when you're doing these labs is like, well, I have a 4-bit width. I want to use all these variables. You actually don't need to use any variables for that. You can just directly use the reserve variables that they have. I'll walk through kind of just like a basic overview of what's happening here. We're gonna have quiet Siri. We're gonna have 10 switch inputs and 10 LED outputs, and we're gonna use this continuous assignment, this data flow level of Verilog, and we're gonna use the assign statement. So that we're essentially doing exactly what they had in the lab, the example, but we're just making sure we have 4 instances of it. I wouldn't say instantiations, but instances of it. And I've kind of used some comments over here to keep it true. So again, we have X allocated to our switch 3 through switch 0, and our Y switch 7 through switch 4, and we want, when the switch is turned off, we want it to output the value of whatever we have on our X switches, and when the switch is turned on, or logic level 1, we want it to output whatever our switch values are for Y. What I do here is just, I don't want to use any of these LEDs, so I've just grounded them. And the last thing we need to do is just, based on our switch 9, if that's logic low, the LED 9 shouldn't be logic low. If it's logic high, then the LED should be logic level high. Cool. So let's save this, make sure that is there. And let's see if there's any like best practices. Okay, so before we actually compiled everything, and then we got all these different errors. But now that we know about pin assignments, let's make sure we make our pin assignments. So I am going to input these. And remember, there's like a quick way and a slow way of doing this. You don't want to be stuck entering them one by one. So we're going to use our Tcl Console, and I have these already ready to go from my .qsf file, which is your Quartus settings file. Okay, boom. So if you're wondering like how I had all these already, maybe go back to the previous video. We had a couple of different ways to prepare these files. So all right. So we have all of our pin assignments done. So we should be ready to compile. Alright, so if you're coming back, I actually compiled and I had an error. So well, maybe let's take a look at this. So if you do get an error, don't freak out. Just take a look at it. So our top level design entity lab 1 part 2 is undefined. So essentially it's not referring to anything. This is why I said like be very consistent with your naming conventions. So my top level is my lab 1 part 2, and if you look at my source file, it actually in my top level module it says part 1. So that needs to be part 2. So let's save that and let's try again. Okay, I will pause here and or fast forward. Alright, we're coming back, so everything compiled successfully this time. So I'm going to take one kind of a look at something deeper in our project, just something cool. So if you actually come to your task section, let's take a look at a little deeper look once we've analyzed and synthesized everything. So we want to look at what does this actually look like, So let's look at our state technology map. Sorry, we don't have any state machines. So if you go into this area, this actually shows you how it's actually implementing this and how it's going to upload it to your board. So there you see your switches. You see a number of buffers. So those are used for timing and reducing the likelihood of you having a timing error. And you have a bunch of your LEDs. So this kind of just displays what the IDE is interpreting from your Verilog file. So something kind of cool. We don't really need to do any timing with this because it's so basic, but just wanted to show that real quick. So as always, want to make sure we don't have any warnings or errors that will prohibit us from moving on. So this error, so it's saying, hey, you don't have anything with timing analyzer, but that's not gonna stop us. We should be pretty good. A bunch of warnings. Let's see if anything is concerning. Yep, that's what we assigned it to be. Okay, looks like nothing that's really concerning here, so that's good. So let's carry on. And let's program. So as I mentioned, you can program from 2 different sources. You can go over here, which is great, or you can come to this button here, also, which is great. So let's see. We don't have any hardware, so that means I haven't plugged it in. So let me plug this in real quick. Got that there. Okay. And I don't have any power. That's why. One sec. And we're back. Okay. So now that I have power, I need to set up my hardware. Okay. So once we see it there, that's great. Let's detect it. Again, we select our device that we want to target. Let's add our output file. So you can find that in the output file section, .sof file. And looks great. I'm just going to remove the excessive one so we have exactly what we want. Let's start programming it. And we see our progress successful. And I will show a close-up of what is happening. So let's select our values first, and I'm going to show a close-up of this so that it makes sense. So I'll just explain it and then you can see it. So I'm going to select certain values of over here. I'm going to select certain values for x. I'm going to select 0 or 1 0 1 1, and then for y I'm going to select 0 0 1 1. So as you can see here, I'm going to toggle the switch output, and then you'll see that when it's 0, it outputs the x, whatever we have on x, and then when we switch it to 1, it'll output whatever it was. So looks like it's working as intended, and everything's good. So yeah, that's all I had for this lab. That's lab 1 part 2. Let me know if you have any questions. Awesome. That's all I had. All right, take care. Bye.